So good morning everyone. Today we will start with basics of digital filtering. I will be hushing down the thing because already your course it started late, and then again we had this thing. We have two more holidays on Tuesdays, so we'll be missing two more classes. So those who are not able to understand, please go to the YouTube channel and see the last year's PPTs. Okay, there you will be getting everything in a detailed manner. Okay, so today I will be hushing down. Okay, so talking about the sampling, we already had talked about the sampling. Okay, however, in the previous video, in the previous lecture, you will be getting a detailed understanding what is sampling and how it can be correlated with the biomedical signals. Okay, so I am not covering this, so please go to the because I have already covered this sampling and all these things in signals and systems. Okay, so we have also talked about these unilateral Z transforms, right? We have also talked about bilateral Z transforms. These are just the extensions, and we have also discussed. Suppose we are having a series of numbers, and then how we can just convert it into the Z transform. Okay, so then comes when we are trying to design any filters, there are certain operators, and these are the three main operators. The first one is the delay operator. Okay, second one is the multiplier, and third one is the adder or summer. Okay, so delay, what it does, suppose you are having xn almost this thing, and you are having xn, then you pass it through delay like this. So let us take up this example. So suppose at the first instance 0, we gave over here xn is 1, so over here we will be getting 1. If we give the same input over here, so when xn is 1, it is delaying the signal. That means this signal will be coming up in the next instance, or in other words, in the present instance, what it will do, it will take up the previous value. So what is the previous value of 1? There is nothing, 0, so we'll be getting 0. Okay, then in the next one we will be getting 2, whereas in the second case we will be getting 1. This one will be coming over here. Then in the next instance we will be getting 2, whereas in the first case we will be getting 5. Okay, in the next instance, in the second case we will be getting 5. So if you see, at the current instance, in the second case, when there is a delay, we are getting the previous values. So what this delay operator does, the delay operators, it holds a value by 1 unit time. Okay, it holds a value by 1 unit time. In other words, it holds and then releases the value after 1 unit of time. Okay, am I clear? So multiplier, suppose you have got this xn, say this xn value is 1, and you have a k value, say for example this k is 5. So once this xn comes, and then it goes to the multiplier, the k value is 5, 1 multiplied by 5, so d will be 5. Okay, suppose there are two signals xn, so initially we get the one value, and there is another this thing, say x dash n, uh, whose signal is given by say 5 2 3 1, something like this. So what is the first signal component? The first signal component is 5. Okay, so you will be getting the output as 6. Okay, so it is just adding. So the major concept which had to be remembered is the delay function, and the rest of the things, these are just multiplication and addition. Okay, now you may ask that sir, what happens if there is a negative 5 or something? So negative 5, suppose we can write say gn, it can be written as say a plus b. In case of a minus b, what will be what we will be having? We will be having basically a plus of minus b, right? Because what is b? B are the coefficient. Coefficient can be positive or negative, right? So it can, so this, even the negative form, it can be represented in the form of the addition, right? Next, when we are trying to design a filter, so what happens is that we have talked about anti-aliasing. So we have to realize over here that anti-aliasing cannot be accomplished with any digital filter. So while you are digitizing the signal, during the digitization of the signal, if any aliasing is present within the signal, we will not be able to remove the aliasing from the signal. Okay, that means the signal is already corrupted. We cannot take care of already a corrupted signal. Okay, so what we have to do? We have to raise the sampling rate to twice the highest frequency present. This is the only step which we need to follow to remove any aliasing. Aliasing cannot be removed through the digital filter. I also told you that before digitizing there is an anti-aliasing filter, which is basically a low pass filter which helps us in limiting the band limit of the signal, bandwidth of the signal, not band limit, bandwidth of the signal. Okay, so this is frequently not practical. Therefore, most digital signal processors have an analog front end, the anti-alias filter. Okay, this is what I told you previously. Now, when we will be designing any filter, we have to keep in mind one of the most important point is that number of poles, it should be greater than the number of zeros. Now, I know many of you do not know what are poles and zeros, so we will be discussing that at a later stage in a few moments of time. But you keep this in mind: number of poles, this should be greater than or equal to the number of the zeros if you want to design a realizable filter. Okay. Now, coming to the filter designing by placement of poles and zeros. Okay. So we all know how to represent a vector in a complex plane. Suppose this is a complex plane. What is this complex plane? This is basically a S plane. Okay. Now in the S plane, we are having 2 points. One is Z, one is P. Okay. There are 2 points. Now how I want to represent this vector? The vector is represented by the 2 vectors Z and P. These are the 2 vectors in this plane, and this is given by P minus Z, right? P minus Z. Okay. Now with this point, let us place some poles and zeros. Okay. Let us place some poles and zeros. Okay. So what are these poles and what are these zeros? Okay. Now, say for example, I hope every one of you know the simplest, one of the simplest filter, not the filter, sorry, no, one of the simplest amplifiers. Say for example, the non-inverting amplifier. Okay. Anyone who does not know? Okay, everyone knows. So we have a non-inverting filter. What is the gain of the non-inverting filter? Gain is given by A equals to V0 by V in or V1. Okay. Now, in the non-inverting filter, all the components are real components. Now, over there, if I introduce some capacitance and all these things, then what will happen? This V0 and Vin, these two would be polynomial functions. Okay, and since we are talking about designing a filter in the S plane, the function would be the S. So we can rewrite this modified inverted non-inverting filter as AS equals to VOS by VES, right? So this can be a simple linear equation, quadratic equation. Okay, it depends. So AS, it is also a polynomial. Okay, when we are having two polynomials, say V0s and V1s, which are in the divided form, if we solve that, we will again get a polynomial function, right? So A is also a polynomial function, right? Now here it, when we are having polynomial functions, they will be having some roots also, right? So we can find out the roots of the denominator. We can also find out the root of the numerator. There will be something in this fashion, say z minus say VA multiplied by z minus VB, something like this, and over here say z minus V dash A into z minus V dash B, say for example. Okay. We can get the polynomials in this fashion. Sorry, not z, this should be s. Okay. Now, if you have some solutions, say s minus V dash A, say for example, anything. So if you are having this thing, and if you put the root value over here, replace this thing, so what will happen? S replaced by some roots. So our for the, if we put it in the numerator, the root values, then the V0 S, it will become 0, and what it will do for the AS, it will bring it down to 0. On the contrary, if we put the root values in the denominator, V1s will be 0 and the function as, it will become infinite. Okay, so infinite means we can think the amplitude is very high. Okay, and 0 means it is having a base value. Okay, where the a's value, it would become 0. Okay, now the roots of the denominator, they are regarded as poles, whereas roots of the numerators, they are regarded as the zeros. Okay, roots of the denominator, they are regarded as poles, roots of the numerator, they are regarded as zeros, because the amplitude values are being put to 0 when we put the root values of the numerator in the equation, and if you put the root values in the denominator, then the gain function as, it becomes infinity. Infinity, we can, since it is very high, the value is very high, we can what you call, we can consider this just as a pole. What is a pole? Pole is basically a very long stick, okay, compared to the surrounding. So now you have understood the concept of poles and zeros. What are poles and what are zeros? So when, if you look into the previous case, when we say that the number of poles should be greater than equal to the number of the zeros for designing the realizable filter, that means the highest power of the V1s equation, it should be either higher, its what do you call, its power should be higher, or it should be at least the same as that of the V0s. Okay. Now, if you see, we have put lambda 1 and lambda 2, which are the poles, right? Now, poles, they are represented with x, and zeros, they are represented with just small zeros. Okay. So, if you see, we have put the this poles over here. There is a point P, and these are the vectors D1, and there is a phase. Then D2, there is a phase associated with that. Then for zeros also, there will be a vector and a phase associated with that. Then another vector and another phase associated with that for the second zero. Okay. Now we have talked about this in the normal S plane. However, when we discussed about your S plane, we have discussed where is the frequency? Where is the frequency in the S plane? पॉलिनोमियल सर्कल कहां से आएगा? वो तो Z प्लेन में है. कहां पे आएगा? This is the at the imaginary axis, y axis. Okay. Why I have used this omega? This omega because conventionally we use it as analog frequency, and this omega is used for digital frequency. Okay. So when we are designing the filters, we need to keep in mind that this point P, it only moves on the imaginary axis, because we are only interested in the frequency characteristics. We are only interested in the frequency characteristics. Okay. In all other things, it is not just the frequency characteristics. There is a combination of a real and the imaginary component or the frequency component. However, imaginary axis is the only axis where your values will be dependent on the frequency component only, and the real component would be 0. Okay. So accordingly, if you try to find out this thing Hs, which is regarded as the, which is corresponding to the As, which is the gain of the system. Okay, so this Hs, it is basically regarded as the transfer function of a given system. It is regarded as the transfer function of a system. Okay, so again I told you, Ps by Qs, there will be two polynomials over there. We had V0s and by V1s. Then we can have some scaling factor. Okay, so that scaling factor can scale the amplitude values that can be there, and then we are having two polynomials. Okay, see, s minus lambda 1, s minus lambda 2, s minus 2 up to s minus lambda n. Here we are having only, we have shown only two poles and two zeros. So you can consider s minus lambda 1, s minus lambda 2, s minus z1, s minus z2 up to s minus zn, the numerator, right? So in both the cases we have got the polynomials. Now, as I told you, we are just interested in the point P. We are just interested in the point P, which should be lying on this imaginary axis. Sorry. On this imaginary axis. So we have to put this P onto the imaginary axis. Okay, so when S is equal to P, this equation converts to this form. Okay, now over here we have put it into the rectangular format. Now if you want to go for this coordinate format where we have this radius and the phase components, so over there we have this r1, which is the distance or the length of the vector multiplied by e to the power j phi 1, the phase associated with the 0. Similarly r2 multiplied by e to the power j phi 2 up to rn e to the power j phi n, and similarly in the denominator. So if you look again from here to here, so what we are having, Bn equals to R1 plus multiplied by R2 multiplied by Rn divided by D1 B2 Dn. Okay. Then we are having this e to the power j. If you simplify this, we get phi 1 plus phi 2 plus this thing up to phi n minus theta 1 plus theta 2 up to theta n. Okay. Now modulus of h of s, it is given by this. This is the real component. Okay, so this is the modulus. So what is that? Bn multiplied by product of the distance of zeros to p divided by product of distances of poles to p. Okay, what would be the phase? The phase would be phi 1 plus phi 2 up to phi n minus theta 1 plus theta 2 plus to theta n. So that is sum of zero angles to p minus sum of pole angles to p. Okay. Now one of the simplest filter is a single pole filter. That means there would be no zero. If there is no zero, then this component will be cut out and you will be getting a the phase component as minus theta. But the thing is that we have considered this for only one point. We have considered this for only one point. If you remember the S plane, we are having real and imaginary real component and imaginary component, right? So the p values, the frequency value, it is starting from 0 and it is going up to infinity, right? Now at each and every frequencies, the p has to attain that value, and then only you will be able to get the frequency response to the filter, something like that, right? So say at 0, 1, 2, 3, 4, in between also, because that is a continuous time signal gain for the इसके लिए. So over there you are having 0.0001, then 0.001, like that. In between also you will be having the thing. So your frequency value, it should be varying from 0 to infinity. Okay, it should be varying from 0 to infinity, so that you get a response something like this, where you will be having a frequency and the amplitude. Okay, any doubt? No. Okay, so this is the single pole filter. So let us take this example. So in this single pole filter you are having this pole. Okay, so our hs, it would be given by 1 by d dash. So when I told that we are having a single pole, you have to keep in mind, whenever you are putting something in the complex domain, there should be another complex component also over there. Okay, the conjugate component. So for this pole there should be another pole in the conjugate domain. Okay. Now what happens is that if I have to find out the frequency response, first I have to start with 0. Over there, the distance of the original pole and the conjugate pole, it would be nearly similar. So this Hs, it would become nearly equal to 1 by d square. Okay. Now slowly, as we move to the shortest distance, which is basically the parallel to the x-axis point from the pole to the frequency axis, at that point we get to a shortest distance, and the distance from here to this point will be quite big. Okay, so as we are going towards this frequency, we see that this d dash value, it is having a larger and larger value, and since it is having a larger and larger value, its contribution to Hs, it is minimum. Okay, its contribution to Hs is minimum. So for the sake of understanding, when we do the calculations for making our life easier, usually we do not use this conjugate pole for the calculation purposes, conjugate pole or the conjugate zeros, whatever, right? So let us forget this conjugate pole now, and let us just concentrate on the pole which we are discussing, the which we have placed. Now if you see, when you put over here, it is having a certain distance, it will give you a certain value, so say something like this, and this value will be increasing up to j of omega naught, where we are having the smallest distance over here, right? So 1 by d, when d is smallest, Hs, it would be the highest. So we come to this point, highest amplitude point, and this omega naught, it is regarded as the resonating frequency of the amplifier or the filter. Okay, resonating frequency of the amplifier. Okay, again, as you go away from this point, the distance again starts increasing to the frequency components, and it starts to die down. Okay, at frequency tending to infinity, there would be some distance, it would not be zero. Okay, so what will be having, this amplitude value, it would be tending to 0, it will be very high. Okay, so the amplitude Hs value, it would be tending to 0, it will not be 0 but tending to 0. Okay, now correspondingly I told you about the phase responses. If you look into the phase responses over here, 0 to minus pi, within this range it will vary, and if you see, it is in the negative domain, because if you see over here, the phases of the poles, they are being subtracted from the phases of the zeros. So if no zeros are present, then we only get the negative value. So, and as I already told you, for one pole filter, it will be minus theta 1, and at each frequency this theta 1 will be changing. So you will be having this thing, you will be having the phase response, something like this. Now the next this plot, it is for a 1-0 filter. Let me tell you, what we discussed is that number of poles should be greater than equal to the number of the zeros to design a realizable filter. However, here if you see, we have designed a single zero filter. This is not realizable, but we want to just understand the effect of zeros. Just for the sake of understanding, we have created this example. Otherwise, this example does not hold good for designing a realizable filter. Okay, you're getting my point? किसी का कुछ प्रॉब्लम है तो बताना अभी. Similar logic what we applied in the single pole filter, the similar logic will be applying over here. We are having R, so HS, it will be dependent on R. The larger the distance, at 0, see there is a large distance, we are having a some particular value, and as we are going down and going up towards the j omega naught, the distance is reducing. Since the distance is reducing, your amplitude value is reducing, and again beyond that it is increasing. Okay, phase response signal 0, it is in the positive half. Okay, that is in the positive half. And if you see the phases, it varies in the range of 0 to pi and 0 to minus pi. Okay, now suppose in both the cases, what happens if I move this, place this axis across, place these poles along the line of the j omega. What I mean to say, suppose I place a pole over here, I place a pole over here, say A, B, C. So what change you will be expecting? If you see the pole at A and its distance from this pole to j omega axis, it is very small. It is very small. So what will happen? The gain will be highest. As we move to B, it will be slightly lower than A, and as we move to C, it will be the gain will be this height, it will come down. Okay. Also, if we place a pole on the frequency axis, distance becomes 0. Since the distance becomes 0, HS becomes infinity. So at that time, our filter becomes unstable in nature. Okay, at that particular frequency, the filter becomes unstable in nature. So while designing any filter, you have to keep in mind that all the poles, they have to be placed in the left hand side plane of the S plane. Okay, not even onto the imaginary axis. If you place the pole onto the imaginary axis, the pole will make the system unstable in nature. Okay, whereas if you see, if you place a 0 at A, B and C locations, what will happen? At A, we will be having the maximum suppression, B will be having something like this, in C we will be having something like this. Okay, we will be having something like this. So nearer the pole or the 0 towards the frequency axis, highest will be their activity. Okay. Now again, if you place the 0 over the frequency axis, it will bring down the amplitude value at that point to 0, and we can analyze the system. It is not becoming infinity. Okay, and due to this reason, the zeros can be placed on either side of the Z plane, on anywhere on the Z plane, not either side, anywhere on the Z plane. So zeros can be placed anywhere on the Z plane, poles have to be placed on the left hand side of the S plane. Okay, and the third proposition is that we will be having this number of the poles should be greater than equal to the number of the zeros to design a realizable filter. Okay, so yeah, 10 minutes we have. So we have this double membrane concept. Now this is a qualitative method to analyze the response of a filter. Okay, many of you don't know how to analyze the filter, how to design the filter, but this rubber membrane concept, it would give you an idea. If you place a pole somewhere, how would the response look like. Okay, so what it says is that you have the S plane, and over this S plane you have put a rubber membrane. Okay, you have put a rubber membrane. Now if you place a stick just beneath the rubber membrane, so what will happen? Suppose this is the rubber membrane, I have inserted the stick and it is just like that. So what will happen? You will be having a cone like this. Okay, you are having a cone like this. Now suppose this edge of the table is your frequency axis. Here is your this thing. So I am looking into this part. Okay, so what is happening? Now I will be cutting this. Now I will be cutting this across this edge. Okay, now when I cut this across this edge, I am having an amplitude over here, right? So that amplitude, it is corresponding to the amplitude response of your system. Now if I move it slightly here, if you see its amplitude level, it has come down. If I again move it further, there is nothing I am cutting. Okay, so this is what it has been shown over here. So as I told you, suppose here you are having this j omega axis. When you cut this, so this is your amplitude level. If this pole is nearer to your j omega axis, suppose at this location, here I cannot move this what you call triangle or this cone. So I am moving this j omega naught axis. So please try to correlate with that. So if the j omega naught axis is nearer to the pole, if you see, this value is higher. And as we are moving this pole away from this j omega naught axis, this amplitude value which is cutting the cone, that amplitude value, it is reducing. Okay, and this is what we have represented over here. So you are having this say pole and this base area of the cone, and from here we have cut this base area. Now if you see, this is the cone. Okay, now you will be getting something like this, and if you straighten it up, you will be getting a filter something like this one. Now just by placing this thing, what you have done, you have created a low pass filter. You have created a low pass filter. Now similarly, if you want to create a high pass filter, you take two poles, say this one and this one, at a higher position, and you apply the poles over there. So that will allow you to design the high pass filter. Suppose you want to design band pass filter. So same thing, we have applied two poles over here, band pass. So Above one of the poles we will be placing a 0, beneath this thing we will be placing another 0. So it will be giving us a band pass, because over here the amplitude will be quite low, and suddenly from this 0 there will be an increase in the amplitude level, and then again it will come down to 0 over there. Then band reject filter or band stop filter, you will be getting something like this. You are having two poles, and between these two poles you put the zeros where the amplitude of the filter will be brought down. Okay, so it will be, the band pass filter would be something like this. Okay, and its corresponding response, it would something look like this one. Okay, then notch filter. So same thing, x notch filter means single frequency compression. So only 1 0 at where you want to suppress the noise. Okay, so that would be the notch filter, and this is the band pass one single pole, dual pole. So it can be either in this form or this one. Here we are having two poles because we have two zeros over here. So band pass filter would be something like this. Its frequency response, it would look something like this. Okay, it can be again, as I told you before, the two poles can be placed separately also. Okay, so this will help you in increasing the bandwidth of the filter, whereas if you use dual poles at the same place, what you will be having is that you will be having a central frequency where there will be a high value. Okay, now if we design a low pass filter and if we design a high pass filter, using those things we can design band pass filter and band reject filter. Okay, so while designing the band pass filter, we have to remember that frequency of the low pass filter, band pass filter, the frequency of the low pass filter, it should be greater than the frequency of the high pass filter. On the contrary, if you want to design band reject filter, then the frequency of the low pass filter should be smaller than the frequency of the high pass filter. So this is a low pass filter, this is the high pass filter. What is the cutoff frequency over here? This is FC and this is FH. On the contrary, if you see over here, this is your FC and this is your FH, high pass filter, right? So with this I will stop today. I don't think I will be having much time to proceed. If you have any questions, we can discuss. Please go through these lectures, okay? Because if you don't understand this, it will be difficult for you to understand the designing of the filters at a later stage.